Christopher Nolan's iconic movie promised to take us to the stars and beyond on the wings of reality. But even the best ones make mistakes when it comes to space physics. So what did he do just right, and where did he fail? And how Stephen Hawking can solve one of the biggest paradoxes of the movie. Let's find out together. Einstein bridges, or otherwise known as wormholes, are tunnels through the fabric of space and time that connects distant places in the universe. So far, we have never actually seen one, but their existence is a possibility both technically and mathematically. It all comes from the world-famous general relativity. Kip Thorne and his colleagues spent decades to prove that wormholes can't exist, which is also the professor's personal belief. But so far, they have failed, according to his words. Meanwhile, the one existing in the movie is not out of the realm of science, and the same applies to the visualization of it. The appearance of the hole and the spotted lights of the other galaxy is also absolutely true to our best scientific knowledge. Of course, it's no wonder, as the crystal-like shape as it appeared in the movie was generated based on real physics simulations run by Thorne and his team. So all of that was pretty solid, but only in a theorist sort of way. Why, you ask? Because the possibility of the existence of wormholes doesn't mean that they can be fabricated, or at least to our knowledge at the moment. To open a wormhole, you would need what's known as negative energy, an energetic state less than zero, but sadly, no sign of it has ever been spotted yet. But for the sake of the movie, let's say it exists. After all, it's a possibility. Great news! We have just opened a wormhole. It's time to fly into it. And this is where it gets complicated and a bit speculative. Except for one thing, and that is traveling time. According to Kip, this is where the movie keeps the biggest distance from real physics. Based on Thorne's simulation, the whole trip would look something like this. Not a big deal, right? Well, now you understand why Nolan made the wormhole scene way longer and much more energetic. But there's one more thing that nobody seems to talk about. It takes a massive object to generate a gravity field sufficient to fold space-time in half, and the one in the movie would have to be the equivalent of 100 million of our suns, according to Princeton cosmologist J. Richard Gott. Depending on where in the universe you placed an object with that kind of mass, it could make a real mess of the surrounding worlds, but it doesn't in the movie. Anyway, Cooper and the crew made it through somehow. On the other side of the wormhole, they come to see Gargantua, a 100 million solar mass black hole at its best. To understand how great work had been done by Thorne and his team when it comes to their simulations, see this comparison. On the left side, you can see Gargantua from the movie, and on the right side, humanity's first ever picture of a black hole 5 years later. Black holes, like all massive objects, bend space-time around them, which in turn bends light around them. This is called gravitational lensing, and we see it when light from behind the black hole is bent around it in an Einstein ring shape. Depending on how you approach the black hole, you could definitely see a bright halo around the hole, as well as light from an accretion disk of matter swirling into the black hole. Needless to say, the movie was more than spot on visualizing the black hole. However, there is a bit of a problem with Miller's planet, the one that orbits Gargantua. Some theoretical physicists may argue this point, but the possibility of a planet like that in the film existing in real universe seems highly unlikely. Despite the fact that scientists are familiar with the concept of innermost stable circular orbit, aka ISCO, which is the last stable circular orbit with a minimal radius for an object revolving around a black hole. We'll get back to this in a moment, but for now, let's see how the trip went. Time spent on Miller's planet comes at great cost. According to the movie, 7 years passes on Earth for every hour spent on the planet. Nolan and his crew were accurate again. Time dilation is a thing. It's been proved many times over. For every 100 years, a person on Earth becomes 1 second younger than an astronaut on orbit 6,200 miles away from the planet. Cooper and Brand were on Miller's planet for a little over 3 hours while Romilly was on orbit, and that cost him 23 years in the movie. Note that time only slows relative between the two groups of people. If we assume the Endurance spaceship that Romilly is in has an equal gravitational potential as that of Earth, 23 years will also pass for people on Earth as well. No one actually experiences anything in slow motion. If Cooper would have sent a GoPro video of the whole trip to his daughter, she would have seen a 3-hour clip or so, with no other differences. However, if Cooper would have live streamed it through a periscope, Murph would have seen everything in ultra-slow motion, receiving a few bits every week. So the scenes are correct, and so does the math. But to suffer that much time dilation, Miller's planet must be traveling at over 99.99% the speed of light. However, such great speed only occurs if the planet is very close to Gargantua, which is certainly not the innermost stable circular orbit. Being that close to a black hole would have hugely adverse effects on the planet, and it would almost certainly have been ripped apart by something called the tidal force, the difference between the gravitational pull on the near side of the planet versus the far side. Hence, no matter how good the tsunami-like waves looked on the screen caused by Gargantua, it is very unlikely that such a planet could exist. So all in all, when it comes to space physics, this part of the movie seems a bit far-fetched. Later on, Cooper decides to fly his ship into Gargantua and didn't die. What's more, he was able to send quantum data back to Earth through space and time in a 5-dimensional tesseract. Most people got very furious because of Cooper surviving the fall and all that happened afterwards. But before judging, hold on for a sec, as there's science to these happenings and some of them are quite confusing. So let's try to unravel the threads. If you think that anybody or anything that gets too close to a black hole gets spaghettified instantly, you're right. Or maybe not. Crossing the event horizon of a black hole is certainly a point of no return, and it will most likely result in a nasty end, but it may not happen immediately. Most people would agree that a person who jumps into a black hole is doomed, says Columbia University cosmologist Brian Greene. But if the black hole is big enough, you wouldn't get spaghettified right away. That's a small comfort, but for a good screenwriter, it's all the speculative room you need. As crazy as it sounds, the movie makers remained faithful to scientific truth, but blended some good old Hollywood-style speculations into it. But that's all. Meaning that one of the most hated acts in the movie can be true. Even Neil deGrasse Tyson told that he didn't particularly like this part, but he couldn't fight it, as we don't know what lies beyond the event horizon. But what about the quantum data? How Cooper was able to send anything out? The accepted truth about a black hole is that its gravitational grip is so powerful that not even light can escape. That's true, but even physics may have loopholes, and this is where Hawking radiation comes into play. To put it simply, when a particle falls into a black hole, the happening creates a form of negative energy. But nature is fond of balance, hence, the black hole emits a particle to keep all the revenue neutral. Millions and trillions of these particles can be capable of carrying encoded information as outflowing energy, just like any of your wireless stuff is doing.